So let's recall some of the definitions from last time. I'm not going to write all of them up, but we'll write down some major definitions. So let's let V, W be vector spaces. That just means metric spaces where you have this additional operation of addition and scalar multiplication. And then a function L from V to W is linear if you can break it up over addition and scalar multiplication. You can write that as a single equation. L of alpha x plus beta y is alpha L of x plus beta L of y for all alpha beta in. We're working with real vector spaces. You can also talk about complex vector spaces. And all x, y inputs in V. And we say that f, a function from V to W, is affine if f of x is W naught plus L of x for some constant W naught, that is some element W naught of W, and some linear function from V to W. Affine functions are what you used to call linear functions back in high school, but you're not going to do that anymore. You're going to call linear functions linear functions. And linear functions have this very nice algebraic characterization, and affine functions have this, annoying extra constant tacked on. So mostly we try to only talk about linear functions if we can get away with it. Now let's recall our definition of derivative, because after all, that's what we're trying to do in Chapter 6. We're trying to define in a derivative. And this is how we did this last semester. So let's let x be a subset of the real numbers and c be a point in our set. C has to be of both in x, and we're going to require C is a limit point. Of x. Most of the time, x is going to be, say, an open subset of the real numbers, and so, of course, all the points in x are limit points, but if you need more generality, everything we did in most of the things we did in Chapter 2, they work for derivatives at limit points. Then let's let f be a function whose domain is x and whose range is the real numbers. And then f prime of c, as you remember, that's the limit as x goes to c. F of x minus f of c over x minus c if the limit exists. So that's the definition of derivative that we all know and love. And what's the problem with generalizing this thing to higher dimensions? The problem is, look at that, we're dividing by x minus c. We're dividing by a real number. Now, I know how to divide by real numbers, at least real numbers that aren't zero. That's something that That's an operation that we all know and love and learned about in elementary school. I can't divide by a vector. I do not know how to divide a number by a vector. That's just not a thing that really works. So we're going to have to come up with some other way of stating, of defining a derivative. So now let's recall another theorem from a little while later in chapter 2. So this is Taylor's theorem. We're going to take the n equals 1 case of Taylor's theorem because we talked about Taylor's theorem last semester. I should point out that the Taylor's theorem in your book has some typos in it. So here is the corrected version. And we can actually be a little bit more general than we were last semester in the n equals 1 case. So let's have our same setup as for derivatives. X is a set of real numbers. C is a point in X that is also a limit point of X. And we're going to suppose that f prime of C exists. And the conclusion is that then there is a function h which has the same domain as f such that h of C is 0, h is continuous, at C, and we've got the following things. F of x is equal to f of C plus f prime of C times x minus C. And then we add to that x minus C times h of x for all x in X, both equal to C and not equal to C. And there is a proposition that I don't believe we ever mentioned explicitly last semester, but it is in your book. And this is essentially saying that this n equals 1 case of Taylor's theorem is an if and only if statement. So we have that f prime of C exists if and only if there is a number D in the real numbers. D, as it happens, is f prime of C, but the statement works for an arbitrary real numbers and a function with the same domain such that h of C is 0, h continuous at C, and exactly what we saw for Taylor's theorem. F of x is f of C plus d times x minus c. And then we add x minus c times h of x. And let's notice this is sort of much nicer than the thing with the limits and the division. And no, we don't have to write down limits explicitly. We can just talk about continuous functions, and from our metric spaces from chapter 5, we know how to talk about continuous functions. So this piece of things, notice, is linear. At least it's linear in the variable x minus c. This whole piece, this bigger piece here, this whole thing at the start is an affine function, constant plus linear, and you know what the constant has to be. It has to be f of c. And then this leftover piece here, this is a continuous function. And also, we know what h of c has to be. It has to be 0. Well, I know what all of those things are. I know what a linear function from the real numbers, from RP to the real numbers is. I know what an affine function is. I just add a constant. I know how to deal with a continuous function, and I know what number in the real numbers I want to say is 0. The only thing that's a real problem is this x minus c business, because now, if I'm trying to generalize this to working over RP, I'm going to need I don't really want to be multiplying by vectors if I'm dealing with functions mapping into RP. So now let's go ahead and write down the definition of the derivative of a function that goes from Euclidean space to another Euclidean space. Definition 6.2 in your book is just functions from RP to the real numbers. It's not until section 6.5 that your book gets around to functions from RP to RQ between two different Euclidean spaces. But I think some aspects of the definition will be a little clearer if I can point out to you how we're going to want to generalize this later. And we've certainly reviewed enough linear algebra that you can see, that you can understand the definition. So we start out with a subset, not of R anymore, but of Euclidean space RP. We grab a point in our set. C is a limit point. Of X in the sense of definition 5.3.13, that it is if R is greater than 0, then you take the ball centered at C of radius R, you delete the point C, the point in the middle, you intersect that with X. So every ball of positive radius contains a point in X that is not the middle point. And then we're going to let f be a function whose domain is X and whose range is RQ. For the rest of section 6.2, Q is going to be 1, but we will eventually get to the case where Q is also allowed to be bigger than 1. And then we say that f is differentiable at C. If there exist some functions L and F such that L has the same range as little f. It's going into RQ. Its domain needs to be a whole vector space, so its domain is all of RP. And L is going to be linear. And F has the same domain and range as our little f. We're going to specify that f of C is 0, by which I mean the 0 vector. If Q is 1, I just mean the number 0. Otherwise, I mean the vector, all of whose entries are 0. It's the additive identity. It's the thing you add to other numbers without changing them. It's the vector you want to be 0. And we also want f to be continuous at C. And we know how to define a continuous function from RP to RQ, or from X to RQ. We know how to define a continuous function on a metric space. We saw that in section 5.4. And okay, what else do we need to be true about these special functions L and F? We want our original function f. We want to be able to write it in a very special way, in the way you expect. F of x is f of C plus L of x minus C. This isn't L times, this is L of now, because now L is a linear function. And then we'll have big F of x at the end. Now, our special case of Taylor's theorem, our proposition 2.2.9 had just x minus c here. But let's think about this for a moment. F of x is in RQ. F of c is also in RQ, because that's the range of f. L of x minus c is in RQ. F of x is in RQ. Okay, all that's great. I don't want to try multiply an RQ function like f by an R or p function like x minus c. I don't want to try multiplying vectors by other vectors. I mean, you can do it. You can make up ways for that to make sense, but I don't want to do it. I would rather multiply by a scalar. So what I'm going to do is, instead of multiplying by x minus c, I'll multiply by the norm of x minus c. And for those of you who remember chapter 5 very well and aren't entirely comfortable with norms, remember that the norm of x minus c is the distance from x to c. That is a real number, and I am totally okay with multiplying vectors, in this case big F of x, by real numbers, in this case our norm. This, of course, is supposed to be true for all x in R set x, our subset x of Rp. If it's differentiable, it has a derivative, so we're going to give that a name. So we're going to say that f prime of c, actually most of the time now we're going to write this as df of c, rather than with a prime we'll use a big D. Now df of c we're going to say is L. So this is the really weird part of the definition. L is not a number. It's not a vector. It's not a matrix. It's not anything like that. This is, df of c is a function, a linear operator, and that's a little, and it's entirely normal if you think that's a little strange. The derivative is a function now, not a number. How weird is that? Well, here's why we want to do this. So if we're going from R to R, notice if P is Q is 1, then this is just proposition 2.2.9, where L of y is equal to f prime of c times y. So that, remember, the only kind of linear operators we have from the real numbers to the real numbers is just multiplying by a constant. So L of y is f prime of c times y. It's not too unreasonable to associate L with the derivative that's a number that you know it love. You have to tweak your h a little bit to account for the fact that you're taking absolute values up here, absolute value of x minus c instead of x minus c, but you can redefine in h, you can let h twiddle of x is h of x if x is bigger than c, and minus h of x, x less than or equal to c. If you redefine h in that way, then your absolute values, then you can have absolute value of x minus c instead of just plain old regular x minus c. Let's do a couple of examples of derivatives. Let's let f of x be, let's say f is a function from, we'll use R2 mapping into the real numbers, be given by f of x1, x2 is going to be x1 squared plus x2 squared. And then we'll subtract off 3 times x1 minus 5x2. And then we'll go ahead and add 7 just to make things interesting. Then I think I'm going to start using a special color, orange, for derivative. df of 0, the derivative of f at 0, of the point x1, x2, that's minus 3x1 minus 5x2. It would be a different number at other places. But you can see this is the linear part of the function. There is your constant, and there is your leftover piece. It should be pretty clear now. Our big F of x1, x2 is going to be the norm of x1 of x, square root of x1 squared plus x2 squared. And it should be clear how that fits into our paradigm as before. F of x is f of 0, which is 7, plus df of 0 of x1 of x that's our minus 3x1 minus 5x2. And then we've got our norm of x minus 0 times big F of x. That's the square root of x1 squared plus x2 squared times itself. Here is another example. Let's let, in this case, f can be a rate function from the real numbers to the real numbers as we know and love. Let's let f of x be, let's say, sine of x. Then here's the graph of this thing, at least on a small interval. Okay, and here is, let's say, pi over 3. This is y equals f of x. Then here's the tangent line that you all know and love. And the thing I want to emphasize is we can write this as y equals f of pi over 3. Then we can add plus df of pi over 3. That's a function. df of pi over 3 is a linear function, remember. And so when we write it df of pi over 3, the function of x, the graph of that thing is just the tangent line. Well, not quite the tangent line. You have to shift it up to get to the tangent line. This tangent line is an affine function, not a linear function. It's often convenient for the derivative to be an actual linear function. But just remember the tangent line is the graph of a function, and the important part of that function is indeed the derivative. So that's another reason why we think of f prime of pi over 3, df of pi over 3, why we think of that as being a function and not just a number. Let's state a not very surprising proposition. This is the proposition that says essentially that differentiation is still a linear operator even with our strange new definition. And proving this is an exam study problem. Let's let x be a subset of Euclidean space. See a limit point that is also in x. As usual, so that the derivative at c, we can even talk about that. And let's say we've got two functions defined from x2, the real numbers, and we're going to suppose that f and g are both differentiable at c, that df of c and dg of c, they both exist. Then if you take the function that is, let's let alpha and beta be two real numbers, then the function, you take alpha times f plus beta times g. That's a function. You just take f of x multiplied by alpha, g of x multiplied by beta, and then add them together. That is differentiable at c. So that derivative exists. And we have that alpha times df of c plus beta times dg of c. That's equal to the derivative of alpha f plus beta g at c. What do I mean by that? That is, if y is in Rp, that is the domain of all these linear operators, then alpha df of c of y plus beta dg of c of y, that's equal to the derivative alpha f plus beta g of c of y. What we're going to do next is we're going to prove a theorem in your book about differentiable functions in multiple dimensions. So we start with our domain. Our function defined on x and our point in x that is also a limit point. Most of the time when you're dealing with differentiability, you want to deal with open sets. That's really where differentiability lives most of the time, but occasionally it's nice to be able to talk about the derivative, at the boundary. So we're going to stick with some differentiability with more general sets. So let's suppose that f is differentiable at c. And the first part of theorem 6.2.12 you can prove in very great generality. Parts B, C, and D we're only going to prove for in the case where x is an open set and therefore x is an interior point. You can draw a little ball around C is an interior point. You can draw a little ball around C where f is defined and so on. But part A says that f is continuous at C. So we have now established, this is saying that all differentiable functions in this sense are continuous, and that is a useful fact. And we recall from your last homework that this is not true for all f such that the partial derivatives exist. So differentiable in the sense that you've got partial derivatives is not enough to enforce continuity, but differentiable in this sense with the linear operators is, and that's a good property. So here is how we prove this. We have that for all x in x, f of x is equal to f of c plus df of c of x plus norm of x minus c times capital F of x. Now, let's look at these pieces. F of c, f of c is a constant function. So we're thinking of f of x as a sum of three different functions. So f1 of x equals f of c is a constant function. So is continuous everywhere. I'm not sure we ever actually proved that, but a constant function from a metric space to a metric space is always continuous. And then f2 of x equals df of c of x is linear. It's a linear function whose domain is Rp is a finite dimensional vector space and whose range is R. So by a proposition in the last lecture, df of c is a continuous function. And by example 5.4.6e, f4 of x, that's the norm of x minus c. Remember, norm is the distance from x to 0, so that's the distance from x to c, is continuous. The distance to a fixed base point is continuous in any metric space, and by assumption, big F is continuous at our base point C. So by proposition 5.4.5, if you've got functions into the real numbers, you can add them up and multiply them, and you get continuous functions. So f is f1, that's the constant, plus f2, plus f4 times big F is continuous at C. So differentiable functions are indeed continuous. So now let's move on to part B. If X is open and J is between 1 and P, then partial J f of C exists. and partial j f of c. I can actually tell you what it is. It is df of c, the linear function, evaluated at the vector ej. That's the vector with zeros in all its regular spots and a 1 in the jth spot. And we can prove this just by writing down the definition, more or less. So recall that partial jf of c, we said in the first video that that's the limit as t goes to 0, f of c plus t times this ej. Then you subtract off f of c, and you divide the whole thing by t. Looks like our limit definition of regular derivative from back in chapter 2. And you can also write it as fj prime of 0, where fj of t is defined to be f of c plus t times ej. And notice that if x is open, then the ball centered at c of radius r is contained in x for some r greater than 0. So fj is defined on the interval from minus r to r for some r greater than 0. So we can at least potentially differentiate this thing. Then let's just write this out. fj of t, that's f of c plus df of c of, what do we have to plug in? We have to plug our input in, c plus tej at tej. Then we have to add to that the norm of tej times big F of c plus tej. And then a couple of things we can do, because df of c is linear, we can pull our t out front, all the way out to the front. And then we're just left with df of c of the vector ej. That's a constant now, it doesn't depend on t. Then our vectors ej have length 1. So t times ej has length t. So we can replace this norm by just a regular old t. And then this f of c plus t ej, you can show that is a function of t. You can even you can put the absolute values around the t if you want. And it is not hard to show that f twiddle is continuous at 0. That is, if Tn is going to 0, then the distance between c plus Tn ej and just regular c, that's the absolute value of Tn, is going to 0. So this sequence is converging to C. So that means big F of, that means F twiddle of T, that's big of Tn, big F of C plus Tn Ej. By our definition of continuity in section 5.4, that's converging to F of C, also known as F twiddle of 0. So we've got a constant F of C. We've got T times a constant df of C of Ej, and then we've got T, or its absolute value, doesn't matter too much which, times a function that's continuous at 0 and equals 0 at 0. So now we've got that Fj satisfies all the conditions of proposition 2.2.9, which is the one saying that our new weird definition of derivative just coincides with the old definition of derivative we know and love from chapter 2. Fj is differentiable at 0, and what it equals is df of C of Ej. Part C of this proposition is that if X is open, then I can tell you what df of C has to be. Df of C of any vector y, it's the inner product of y with the gradient of f at C, where grad f of C, that is the vector of all the partial derivatives. And the proof is quite straightforward. It's just by proposition 6.2.8. If you've got any linear operator, you can always write it as the inner product of y with A, where Aj is your linear operator evaluated at Ej, which in this case, we just saw in part C, is the partial derivative at C. And then the last part is that if X is open, then the derivative is well defined. There is there's only one linear operator, L, that satisfies our conditions. That is f of x equals f of C plus L of x minus C plus our error terms. So at least for open sets, the derivative is well defined. There's only one linear operator that can be df of C. And that's not always true if x isn't open, if C isn't an interior point, and you'll look at that a little bit on your homework. We prove this, of course, by noticing that part C tells us what df of C has to be. The only thing it can be is the inner product with the gradient.